we just have to go on Monday? Like, sure.
Someone else look.
You guys have access to the same page?
Yeah, like presentations.
Look, you are the worst.
We still have to do it. We still have to do it.
Let's go.
Jesus Christ.
It's just a lot more material this time around. Because I plan on it. Because I wanted to study it. There's a lot of things that could be. So I was going to go home and take that afterwards. Because I don't want to wait till tomorrow.
Okay.
I'm not worried about it too.
That is. Yeah, that's what you said Friday.
I could have been. Let's go to it.
I don't know. We only have 3 weeks on that left. Actually, I would say they had all done well until last week.
Okay, good morning everyone. So this will be the last lecture on radiation heat transfer. From Wednesday we'll move on to convection. Okay? There will be around 9 lectures on convection. We'll cover external convection. We might maybe spend about 1 lecture on internal flow, and then we'll go to heat exchangers. Okay. Alright. So here is the problem. Last problem on radiative heat transfer. So in this problem, we have an ice skating rink, which is modeled in the form of a cylinder. Okay. So I'm going to draw it out, and then we'll have some of these parameters listed. All right. So we have the walls of the ice skating rink. I'm going to call them as walls W. Then I have the bottom, which is ice. Then I have that ceiling, as you can see, drawn in the form of a lid. The ceiling has a bottom surface and a top surface. The bottom I'm going to call by the subscript little c. And the top surface of the ceiling is open to ambient surroundings, so I'm going to call it as outside O, outside of the ceiling. There is some air within the arena, which I'm going to call as little a, so TA, HA. Okay, temperature of the air within the arena, and then I have the convective heat transfer coefficient within the arena. Then ambient or outside, T infinity, H infinity. Okay, this is having a conversation with the top surface of the ceiling or the outside surface of the ceiling, and T infinity, H infinity are the temperature and the convective heat transfer coefficient. You are given the following information. So given, let's start from the inside, the arena. Here are the details. The temperature is 15 degrees Celsius, and the convective heat transfer coefficient is 5 watts per meter square Kelvin. Then you're told that for the walls, here is the information. So all subscript W will be the walls, all subscript little a will be the arena air and so on. So for the walls, temperature is given as 15 degrees Celsius. And the emissivity of the walls, you're asked to treat it as an ideal surface. So epsilon wall is 1. Okay. Then for the ice, which is the bottom, little I, so this is Ti is given to us as minus 5 degrees Celsius. And epsilon I, we have to treat the ice surface as having an emissivity of 1 as well. Then ambient conditions and then sealing conditions. So ambient, T infinity is minus 5 degrees Celsius, and H is the same as the inside arena. So there is very slow moving air both on the outside as well as on the inside. Okay, so I have H infinity is 5 watts per meter square Kelvin. So that's given to us. And then we have the sealing itself. Now here is the issue. If the temperature of the ceiling falls below 9.4 degrees Celsius, first of all, temperature is not known to us. Okay, so this is unknown. But if the temperature of the ceiling falls below 9.4 degrees Celsius, then all of the water vapor will start condensing onto the ice floor. Okay, and this means that as water falls on the ice floor, it will start creating small bumps on the ice floor, and obviously this is not good for playing a game or for skating. Okay, so if Tc falls below 9.4 degrees Celsius, this temperature is actually called the dew point temperature. You might have come across this in thermodynamics. So water vapor condenses and forms what is called as dew, and droplets will fall onto the floor, creates bumps, and this is the thing that we need to avoid. And the owners of this ice hockey rink, they have the option of choosing the nature of the ceiling. They can either have shiny surface on the ceiling or they can paint it brown. So ceiling, you have two options. The first option, if you choose a shiny surface, shiny coating, the emissivity of the ceiling is 0.05, obviously less abrasion, so there is lesser amount of emissive power. If you choose a brown coating, epsilon of the ceiling is 0.94. Okay. And so the choice is okay. Based upon epsilon C being 0.05, there will be a certain temperature of the ceiling, considering the conditions within the arena and outside. Based upon 0.94, there will be a certain temperature for the ceiling. And the idea is, okay, which one should I choose? And this is the whole problem. There is great suspicion that one should not choose this because nobody paints their ceiling brown. But there is also a reason why you should not choose it. is because if the emissivity is very high, it means that there is more heat removed out, there is more heat emitted by radiation, which means that it will leave the temperature of the ceiling to be lesser. So the suspicion is, perhaps this is not a good choice. It is not yet validated by any of the calculations that we have done, and our plan is to do all these calculations. Okay? Furthermore, you are given the following equations for the view factors. If you recall, we had obtained an integral equation for view factor Fij was 1 by Ai Okay, so this was the equation that we had looked at maybe a few lectures back, 3 or 4 lectures back. We don't need to use this equation, but for bodies where it is not very obvious as to how to calculate the view factor, one needs to look at a set of tables where these view factors are calculated for a given geometry of 2 interacting surfaces. So if I'm considering the interaction between 2 cylinders, and now the dimensions need to be given, so this is the thickness, 0.3 meters is the thickness of the ceiling. The total height from the ice onto the ceiling is 10 meters. And then the diameter, 50 meters. It's a mid-size hockey rink. So for 2 bodies that are circular surfaces interacting with each other, the view factor equations can be calculated as follows. Okay, so for this is object I, this is object J. Okay, they are exchanging radiant energy between the two. Their total height, their apart is L. Let's say the radius of the first piece is R suffix I. The radius of the second piece is R suffix J. Then the view factor can be calculated as the following, and this typically, if I have these kinds of geometries, I'll give you the view factors, so there will be a table that will be listed with the view factors. Okay, so here is the equation for us. It is Fij is equal to S minus S square minus 4 Rj by Ri whole square whole to the power 1 by 2, bracket close, where S is the following. Is 1 plus Rj square divided by capital Ri square, where capital Rj and capital Ri are non-dimensionalized with respect to the height separating the two. So Ri is little ri by L, Rj is little Rj by L. So this is unlike the other problems we solved where we were able to discern the view factor without going through any extensive calculations. In this problem you have to make use of the given formula, and this can be given for different types of surfaces. The top could be a circular cross section, the bottom could be a triangle. The view factor would change. Likewise it would change depending on the nature of the surfaces. So this is a geometric measure. so we have a problem on our hands. And this is a problem where several things are taking place. Okay. One more thing I forgot to add, just put it back in here. For the sealing, the thermal conductivity is given to us. Okay, so K of the sealing is 0.035 watts per meter Kelvin. This is the thermal conductivity of the sealing material. Okay. All right. Okay. So how to solve this problem is we have to consider all different types of modes of heat transfer that are taking place. And because thermal conductivity is given, there is conductive heat transfer. There is going to be convection between the outside of the sealing and the ambient atmosphere. There is going to be convection between the sealing bottom itself and the arena air. There is going to be convection between the ice and the arena air. And there is going to be radiation heat transfer between three surfaces. And this is the type of problem you can expect in your final exam, okay, where everything is coming together. All right. So let's get going on this. What are the modes of heat transfer? First is, and I'm just going to list everything down. Convection between the arena air and the sealing. I'm focusing on the sealing because that's where most of our energy has to be spent, because we have to calculate its temperature. Okay, so that's one there. Then I'm going to have three surface enclosure radiation. Surface 1 is the wall, surface 2 is the ice, surface 3 is the bottom of the sealing, which I call as C. Then I'm going to have conduction. Through C, through the thickness, so you're given a thermal conductivity. And the last one is convection between the outside of the sealing and the ambient atmosphere. And if you want, you can also include convection between ice and the arena air. Not interested in it because I already know the temperature of ice. That's -5. Okay. So since our focus is the sealing, let us focus on the sealing. And I'm just going to draw a front view of this entire cylindrical setup. So this is how the setup will look like. So first top surface is O, so temperature is TO. Then I'm going to have temperature of the sealing, TC. Let's say that's given right here. TC. T infinity, H infinity, EA, HA. Okay, so this is the setup. The walls W. And then the ice. T ice. Focus on the sealing. I'm going to draw two control volumes and perform a surface energy balance. Okay, because we need to know what's happening on the sealing. So first control volume. Second one. This is, and that's 2. Okay. And let's draw them out separately on the other panel. You can make the problem a little more scary by putting in some energy generation within the ceiling. It's possible, but we will avoid all that for this problem at least. So if I draw the control volume 1, do the surface energy balance, do the control volume 2, surface energy balance, there is no E dot stored, there is no E dot generation for a surface energy balance. So from 1, what are the modes of heat transfer? I'm going to have conduction taking place. So this is going to be Q conduction. I don't know the direction, I'm just drawing it up. Most probably I'm assuming that ambient atmosphere is colder than probably the ceiling, so there is going to be convection from the top surface onto the ambient. If there is no heat generation, then it means that the heat has to travel from the C all the way to O. This is just an assumption. Then maybe the ceiling is hotter than the arena air, so there is convection between the two. Or maybe the ceiling is colder than the arena air, who knows, really, right? So I'm just going to call this as Q, convection between A and the ceiling, so A and C. Is my nomenclature clear to everybody? All of the subscripts and so on. C for ceiling, A for the arena air, O for outside of the ceiling, infinity for the ambient conditions, I for ice and W for wall. And it is possible that there is also radiation heat transfer. I am neglecting radiation heat transfer between the ambient atmosphere and the outside of the wall because there is no information given to me. Okay? So in this case I'm going to have radiation heat transfer from the ceiling all to the other three surfaces. So I'm just going to call it as Q radiation C. This is all the net radiative heat transfer rate from the ceiling. That's it, coming out of the ceiling. So Q is the net radiative heat rate from ceiling to surroundings. And out of this, some portion will go to the ice, some portion will go to the walls. And that's decided by the view factors that we have. So this is it for surface 1. I'll draw something for surface 2 as well. So this is C here. This is O. There is obviously convection heat transfer from the outside of the ceiling onto the ambient. So Q, convection from O to infinity. And then what else is going on? This is just going to be conduction heat transfer on the bottom face. Q conduction through the ceiling. So we can just give it a subscript Q conduction through the thickness of the ceiling. That's about it for the second control surface, control volume, or surface energy balance. No radiation because there is no information given on radiation between the outside and the surroundings. So if I just write the energy balance for 1 and 2, so from 1, E dot in minus E dot out is equal to 0. There is no stored, there is no energy generated and so on. And so if I write this out, this is just going to be Q convection between the arena and the ceiling. This is plus Q conduction. I'm sorry, this is not plus Q conduction, minus Q conduction. This is leaving. Minus Q radiation is 0. So there's only one thing coming in, the rest of them are all leaving the control volume as you've seen there. Same thing for the second one. Q conduction, that's the one that's entering in. Things that are leaving out, Q convection over infinity. Now one could do a couple of things. You see Q conduction C, I can replace it by this guy. If I write the convection heat transfer equation, if you recall, this is H times area of the ceiling. The top and the bottom surface have the same area, so, and that is just the surface area of a circle, pi r square, radius being 25 meters. So H times A times delta T, which is TO minus T infinity. Does this make sense to everybody? Obviously this is not a good idea because I don't know TO. I'm not given that temperature. I would like to make sure that there is only one unknown in this particular problem or this particular balance that we are performing, and that's going to be Tc, which is the temperature of the ceiling. So since this is not known to us, it is not a wise idea to substitute for Q conduction from this equation. Does this make sense to everybody? Which means we need to find out a different way of substituting for this guy. Okay? And so let's look at it here. Notice, I don't want T out coming into my equations, but I would prefer to have Tc because that's an unknown and that's what I'm hunting for. So I would like this fellow in my game, and this is already known to me. So if I draw a thermal resistance network between the ceiling all the way to the ambient, this is the conduction and convection heat transfer thermal resistance network. This has nothing to do with radiation heat transfer. So if I draw that resistance network, I have the following. Tc, T infinity, I have conductive resistance as I flow through the ceiling, so this is R conduction. And then I have convective resistance as I go from outside onto the T infinity. This is T out, if you would like. And this is R convection. And whatever is the current flowing through the circuit is nothing but Q conduction. I want to make sure this is okay with everybody. This has nothing to do with the radiative resistance network, which we are going to come to next. So this is the key. So rather than use the surface energy balance on control volume 2, which is kind of useless now, I will use Q conduction as the current flowing through these two branches. And so I will write it as Tc minus T infinity divided by the total resistance, R conduction and R convection. Okay, so I'm going to write it out here and then combine it there. So Q conduction C is Tc T infinity or conduction or convection. So this is the substitution I'm going to make. So this is equation 2. This is equation 1. Substitute into equation 1 from equation 2. And I want to pause before pushing this up so that everybody has it. Any questions so far, please? And once you're doing convection heat transfer, right, then what will happen is that this problem can be modified to say, okay, hey, this is not given to me, but I'm given the velocity boundary conditions, and I'm given the velocity profile, and I'm given other information relating to the fluid flow on top of the surface of the outside of the ceiling. Calculate H, then do this, then take all of that and put it there. And this is how a real problem works. It's pretty nasty. Absolutely nasty. And I can do the same thing. I can have internal flow taking place. I can have fluid flowing past the bottom of the ceiling as well within a closed enclosure, but we don't do things like that. We will typically look mostly at external flow and flow through pipes and so on. Okay? Alright, so moving on. Substitute 2 into 1. And the idea is you take something that looks as nasty as this, but you break it up into small pieces, and then you eventually get to some place where it is much more tractable. So substituting 2 into 1, I have Q conduction, A to C, I'm going to do the substitutions of the equations. So I have HA, area of the ceiling, TA minus TC, okay. Then Q conduction, which we just wrote as TC minus T infinity by R conduction, R convection, and watch this. Minus Q radiation C, I'm just going to bring it onto the right hand side and say this is equal to Q radiation C. And why am I doing it? Because this is the person that we know how to treat using the resistive networks in thermal radiation. By drawing those 3 branches and then drawing it in the form of a triangle and then having these fundamental nodes EB, T1, T2, T3, I can actually have an idea of what this creature is. So to isolate this fellow, we are doing all of these things, and it is obvious that this will end up being a function of the temperature of the ceiling. So this is my first equation where Q radiation is a function of Tc. I will have to come up with another equation where Q radiation is a function of Tc. 2 equations, I can equate them to solve for Tc. I should get something that is algebraic and highly nonlinear. Tc to the power 4 and all other things going on. I have the values for these things. So substitute. This is 5. This is pi r square. 5 times 25 square. The diameter of the ring was 50, so this is 625 pi. TA is known to me, 15 degrees. Let me do the substitution for this one particular thing, okay? So I'm going to have 5 times 625. TA is 15. You do not want to write it as 15 degrees. 15 plus 273. When radiation is there, everything has to be in Kelvin. This is 288 minus Tc. This is why I wanted to write it out. Minus Tc minus 273 plus T infinity was 5. So that's minus 5, I'm sorry. Somewhere. So that's 273 minus 5. All of this. Conductive resistance, just to jog back our memories, is the length divided by K times A, thermal conductivity times area. The length is the thickness of this plate, so that's going to be 0.3 meters by 0.035 times 5 times 625. Convective resistance is 1 by H times A, so that's 1 by 5 times 625. So just to refresh memory, this is L by Ka, one by H surface area available for heat transfer. So if I simplify this, I'm going to get something in terms of Tc, and so Q radiation C. I have the simplified version of this here. All of this put together is 9817 times 288 minus Tc minus all of these resistances combined together and then flip back on is 224 times Tc minus 273 minus. Equation 3. Any questions so far? So the basic idea is I don't know TC. I need to operate on the idea that, okay, I have radiation within an enclosure, so we know how to do this using the resistive networks. But there is conduction and convection as well, so we have to somehow bring those into play. We focus on the sealing because that's the area of interest for us. And then once we have the network done, this is one equation. Now the whole ball game is to find Q radiation C using the thermal resistance networks. Okay, so to obtain this, next, we will start off by drawing our circuit. Okay, so this is a three-surface enclosure. This is analysis only for Q radiation C. Okay, that is something to be very, very careful about. Nodes EB, TC, EB, T wall, EB, T ice. These are the three fundamental nodes. Each of them being equal to sigma, Tc to the power 4, and so on and so forth. So this is sigma, Tc to the power 4, for example. Okay, then the next come the three radiosity nodes, each below, one here, one next to it, one next to it. So this is J ice, this is J wall, JC. Okay, and I can push this a little below. Then you join each of them through the resistances. Okay, surface resistances between the fundamental and the secondary nodes. Then the geometric resistances between the radiosity nodes. So I should have this as JC. One more. So this is RC, R wall, RI. These are the surface resistances, each of them. Then I have the remaining ones. Between C and I have RCI or RIC. Does not matter what you call them to be, okay? They are all following the reciprocity rule. So this is RWI and this is RCW. And I'm going to list each of them. So I have RI is 1 minus epsilon ice by AI epsilon I. Then R wall and RC likewise. 1 minus epsilon wall, A wall epsilon wall. And then RC is epsilon C, AC, epsilon C. Epsilon ice is 1. Epsilon of the wall is also 1. Both of these end up being 0. Which tells us, based upon what we did last class, EB is equal to JI. So you can kind of switch off this particular branch. There is no resistance through that branch, so the current is the same, and the voltage across the terminals are also the same. Okay. Then I have this to be 0 as well, which tells me that EB at T wall is equal to J wall, so there is no resistance here too. It's not an open circuit. There is no resistance to the flow of current. We also looked at an idea of where we had infinite resistance in the previous class. Okay, that is not the same as here. So EB at TW is the same as JW, and so these can be written as sigma TI and sigma TW is the power 4. Okay. All right. Then the remaining ones, which are the geometric resistances, I have the following. Now here I have a problem, right? Because I have to calculate it two times. One is for the shiny ceiling and the other is for the brown coating. Okay, so this could be calculated for the shiny, where epsilon c is 0.05, and then the brown coating, epsilon c is 0.94. So I have two paths that I need to follow here. I'll list the geometric resistances as well. So I have R IC is 1 by AI. FIC is the view factor from the ice as intercepted by the ceiling. Or by the reciprocity, this is the same as 1 by AC FCI. Likewise, I have R IW and CW, or RWI is 1 by AI FIW, or 1 by AW FWI, and the last one, RCW. Once again, the primary resistances are the surface resistances, the remaining ones between the radiosities are the geometric resistances. Now you see why the information on the view factor is given to us, because I need to calculate FIC and all these other creatures. So let's go ahead and do that quickly. With your permission, is it okay if I directly write out these view factors, or do you want me to go through the calculations of them? Maybe let me do one, okay? So let's say I and C. Area of the ice is the same as area of the ceiling. Is 5 times 625 meters squared. Okay, that's one. Then Ri and Rc is Ri by L, which is 50 by 2 times 10. 50 by 2 is 25 the radius, so this is 2.5. Then Rj, which I'm going to calculate as Rc by L. I'm using the same notation as what I have in that formula there. Okay, I'm thinking of I as the ice and J as the ceiling. So in this case, this is the ceiling, which is J. This is the ice, which is I in the formula. And this is also 2.5. Once you have Ri and Rj, it is just a matter of substitution, so I'm going to leave it at that. Substitute into the formula to obtain FIC. I is between the ice and the ceiling, but because of symmetry, both of the surface areas are the same. FIC is the same as FC. And it is a matter of just looking at it and flipping all these variables and realizing that. So in our problem, this is the same as FCI because of symmetry. In our problem, this is not true in general. Okay, if you have obviously surface areas that are not equal to each other, then this is not the case. Okay, that's something to be clear about as well. I'm going to get rid of equation 3. I need it, but and how to calculate any of these things. So let's say what do we need here. I know AI, FIC, so this is known to us. Okay, and all these will be posted. I have a whole set of problems that I started off last week, Wednesday, including today's problem. I'm going to post them all together. Okay, these are all the problems on radiative resistance networks. You'll be needing them for your next homework. Then RWI, IW needs to be calculated. So let's look at this. FII, FIC. Use the summation principle. I have three surfaces, so FII, IC and IW is equal to 1. But if you look at the ice, it's a flat surface. It is not going to get any radiation from itself, so this is gone. FIC can be calculated from the formula. So that FIW is 1 minus FIC. So if I know FIC, I can calculate FIW, which means that I know the resistance here. This is known to us as well. And then the last one, CW, same idea. FCC, CI, CW is equal to 1. The summation is made on the second index here. FCC, you look at the ceiling, it's flat, so it is not going to see any radiation from itself. FCI is the same as FIC, so FCW can be calculated. Which means that FCW is the same as FIW. Okay, don't be tripping up on these subscripts, they're just ice, wall and the ceiling. So this resistance can also be calculated. So all of these resistances can be calculated, including this creature, but twice. Okay. What's our next step? I had what was called as equation 3. You can see the ghost of that written here. I need to calculate Q radiation C as well using this network. So how to do that is by doing the following. What is Q radiation C here? Q radiation C is nothing but the heat rate that is flowing through from EB at TC. So this is Q radiation C. And I immediately recognize that this Q radiation C is splitting up into two branches, going one here and going one there. Okay, so that is essentially Kirchhoff's law used there. So Q radiation C, which is first of all sigma Tc to the power 4 minus Jc divided by RC this is, let's call this as equation 4. This is also the same as splitting it up into two more branches and writing it based on the geometric resistances. And I want to see if I can erase this panel off already. Okay, got it? It's possible that we may have to come back and complete this problem on Wednesday, but that's fine. So I have Q radiation C. Please notice, this is Q radiation C, splits off into two branches. So the sum of the current in this branch plus that branch is the same as Q radiation C. Okay, Kirchhoff's law. So if I do that, this is going to be Jc minus sigma T wall to the power 4 by RCW, which is known to us. T wall is known to us. Jc is not known to us. Plus Jc minus sigma Ti to the power 4 by RIC. This is equation 4.